Today we will be discussing about annuity. We use A to designate annuity. This is a series of equal payments occurring at equal interval of time. The types of annuity that we will be discussing today is all about ordinary annuity. We also have the annuity due and the deferred annuity. Each of these types will be discussed later on. Now, first we have what we call as the ordinary annuity. This is the payments occur at the beginning of each period. If you have noticed here our cash flow diagram, this is our annuity at the beginning of at the end of each period. So this is 0 and then we have here 1. So that is end of each period. So we have here a series of equal payment represented by A. We have here our A, and then we have here the present value of this annuity designated by P, and then the future value of this annuity designated by F. Now, to compute the P or the present value, we have here our formula, and then to compute the future value, we have also here our formula. And then if we are going to find the equal payment series compound factor, we have this formula. Okay, so these are our formula when we find the P, the present value, the future value, and of course the equal payment series compound amount factor. Now we have our example so that you can clearly understand what is ordinary annuity all about. Take note, payments occur at the end of each period. So example here, an investment of 250,000 is made at the end of each period with interest of 2.5% compounded annually. Determine the equal payment series compound amount factor after 10 years. So for letter A, we have this formula for the compound amount factor. Letter B, determine the total amount of the investment after 10 years. So probably we'll be using this formula F. We find F. And then letter C, how long in years will it take for the investment to amount to 10 million. Okay, so we are going to solve now letter A. Of course, letter A, to solve letter A, we simply use this formula 1 plus I raised to n minus 1 all over I. Okay, so that is equivalent to, take note, our given I is 2.5%, so we convert this one into decimal, that is 0.025. Simply 2.5 divided by 100, that is 0.025. So we have here 1 plus 0.025 raised to, our n here is of course 10 because we have here 10 years. And then we have here minus 1 divided by 0.025. So that is equivalent to 0.1120, or if we convert it into percentage, that is 11.25. If we use calculator, that is equivalent to 11.20. So that is how we compute the compound amount factor. Now for letter B, determine the total amount of the investment after 10 years. Okay. Now by the way, if we do the cash flow diagram for this particular problem, we have an investment of 250,000 is made at the end of each year. So that will be our annuity. Okay. So at the end of each year with interest of 2 compounded monthly. So letter B, determine the total amount of the investment after 10 years. Okay, so after 10 years, letter B, Of course, we use this formula after 10 years. Okay, so after 10 years, F is equivalent to A. Take note, A, we have this one, times our compound amount factor, which we already solved. So I will just write immediately our solution. So F, for a while. Okay, so F is equivalent to A. We have here our A, which is 250,000 multiplied by our compound amount factor, which we already found it as 11.20. So that is equivalent to 2,800,845.44. Okay, so that is letter B. Now letter C, how long will it take for the investment to amount to 10 million? Okay, 10 million. So that is our future, 10 million. So how long? Okay, we will be using again this formula. So if we make use of that formula, this is F is equivalent to A 1 plus I raised to n minus 1 all over I. Okay, so F here is equivalent to, okay, our F, we will substitute directly the value of F, which is, if we go back to this one, how long in years will it take for the investment to amount to 10 million? So 10 million, that will be our F. And then our A, annuity, which is sorry for that. Okay, that is 250,000. 250,000 multiplied by 1 plus I raised 1 plus I, our I here is equivalent to, we will check the percentage, 0.025. So this is 0.025. 1 plus 0.025 is 1.025. Okay, and then we have raised to n, this is the unknown value, minus 1 all over, okay, all over I, which is equivalent to, our I here is 0.025. Okay, so by the way, this one, okay, so we will multiply 0.025 by 10 million, multiplied by 0.025, and then this 250,000 will be transferred on the other side. That becomes 250,000. So we have 1.025 raised to n minus 1. This minus 1 will be transferred to the other side. That becomes positive 1. Okay, so we transfer this 1 to the other side. That becomes positive 1. And then, of course, the value here, if we compute this value, that is equivalent to 2, which is then equivalent to 1.025 raised to n. Since we have here n, we will apply ln. to both sides. ln of 2, that is n ln of 1.025. Okay, so take note, if we have here let's say x cube, if we apply ln to our variable x cube, okay, then this can be rewrite as 3 ln of x. So this exponent will be transferred here. Okay, that is why for this case n will be transferred here, so that ln of 2 divided by ln of 1.025, that is equivalent to n. So our n here is equivalent to 28.07. That is how we compute our n. Now we will proceed with the annuity due. This is another types of annuity. Payment occur at the beginning of each period. So if you have noticed here, our A is at the beginning of each period. So if this is our year 0, then we have here our A annuity at the beginning of each period. Unlike the previous types of annuity, the ordinary annuity, our annuity starts at the end of the period. So we have our formula for the annuity due, or the present formula for in finding, the present value in finding the annuity due formula. Annuity due when problems involves annuity due. So we have this one as our formula for the present value. We have here our P, and then when we compute our F, this is our formula for finding F. Now we go directly with our example. Find the future value at the end of the last payment period. Payments of 10,000 each are made at the beginning of each year for 4 years. So at the beginning of each year for 4 years. So that means we have our 1, 2, 3, 4. Okay. Payments of 10,000 each are made at the beginning of each year for 4 years with 5% compounded annually. So this is our diagram or cash flow diagram. So we are going to find our F. Okay. This is our A. So our F will be here. So when we solve F, we simply use this formula. So we have our F, which is equivalent to A, series of equal payment, 1 plus I raised to n minus 1 all over I, okay, and then 1 plus I. So we simply substitute our value. So we have here 10,000 as our annuity. 10,000 times I here is 5% plus 1, that is 0.05. So 1.05, and then of course this is raised to 4. Our n is raised to 4, and then minus 1 divided by our I, which is 0.05. So our F is equivalent to 45,256.31. That will be the value of our F, or the future value. Now we have the last type of annuity. We have what we call as the deferred annuity. First payment occurs later than at the end of the first period. So if you have noticed here, our series of equal payment, this one, okay, series of equal payment occurs on year 3 or after year 3. Okay. Now, to explain further, take note in our formula for finding P, we have here n plus k, the exponent. So, we have here our k, okay, this is our k, before the end of year 3 for this case, okay. So, we have here our example. A man loans 670,000 from a bank with interest at 4% compounded semi-annually. By the way, we will make use of annually. Okay. Later on, we will make use of semi-annually. So, okay. So, a man loans 670,000 from a bank with interest at 4% compounded annually. He agrees to pay his obligations by paying 10 equal annual payments, the first being due at the end of 5 years. Find the annual payments. Okay. So, a man loans 670,000. So, this will be our present value. If we draw the cash flow diagram, we have here our 670,000 from a bank with an interest of 4% compounded annually. He agrees to pay his obligations by paying 10 equal annual payments, the first being due at the end of 5 years. So, 1 year, 2, 3, 4, 5. Okay, so this is 5. So, annual, we have here 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10. So, this is now our 10 equal payment or 10 equal annual payments. Okay. So, if you have noticed, our n here is of course 10. And then our k is equivalent to this year, which is 4. So, 4. And then, P, we have here our P. So, basically, we will make use of this formula. So, we have P is equivalent to, okay, I will substitute directly the value of P as 670,000, which is equivalent to our A, which is the unknown value, and then we have 1 plus our I is 0%, 4%, that is 0.04, and then here our N, of course our N is equal to 10 minus 1 divided by I, which is 0.04, times 1.04. I will add directly 1 plus 0.04, that is 1.04, and then raised to our N is equivalent to 10, and then this one, so we have here 14. Okay, so we have here a bracket, and then if we solve this one, we simply multiply 670,000 times 0.04 and then 1.04 raised to 14. And then this negative 1 will be transferred to the other side. That becomes later on, which is then equivalent to A, and then this group will be transferred on the other side. That becomes the denominator. Okay, so we have 1.04 raised to 10 minus 1. So our value of A is equal to, or A, I will just write here our A, that is 96,636. So deferred annuity. Again, as a recap, we have the three types of annuity. We have what we call as the ordinary, the annuity due, and then the other one is the deferred annuity. So for ordinary, we usually start here. Okay, payments start at the end of each period. Okay, for annuity due, at the beginning of each period. So we have this one. Okay, and then for deferred annuity, we have, let's say, later date, series of equal payment. Say for example, this is our P, present value. So this is our deferred annuity. After several years, a series of equal payment occurs. Okay.